Okay, I'm back, and in our previous segment, we introduced the concept of a black body and the black body curve. So, a black body curve is on something like this, where you've got brightness of the light being emitted going up and down, and then the wavelength of the light being emitted going sideways. And remember, when I say the word light, I don't just necessarily mean Roy G. Biv. So, some of the light being emitted could actually be in the infrared part of the spectrum, and maybe some of it could be in the ultraviolet and in the X-ray part of the spectrum. So the first black body radiation law is called Wien's law, and I know it looks like Wien's law, but it's Wien's, and it says that the maximum wavelength of the light being emitted is equal to 0.0029 divided by the temperature of the black body. So that's capital T for temperature. And then you notice the letter for wavelength, but it says maximum wavelength. So the maximum wavelength is going to correspond to where this graph is at its maximum. So that would be right here for this one. It would be right here for this one, and then it would be right here for this one over here. So it depends on the black body as to where its maximum wavelength is located at. So let's just do a conceptual thing before we go on to plug numbers into the formula. So do you notice where the T is? So the T is in the bottom part of the formula. So what would happen if I increase the temperature to a black body? What's going to happen to the maximum wavelength? Is it going to go up? Is it going to go down? Or is it going to stay the same? So what do you think? Okay, the T's in the bottom part of the formula. So if you increase the T, what comes out gets small. The wavelength is getting small as the temperature increases. Now, does that make sense? Okay, let's go back up to here. Do you remember that radio waves had the largest wavelengths? And then over here, the gamma rays, they had the smallest wavelengths. So if the temperature goes up and the wavelength is going down, that means you're shifting in that direction, and that's exactly what happened. So this was the small t, small temperature, and it made this hump, and then this one would be a medium-sized t, and then this one would be a larger t. So as the temperature is going up, the maximum wavelength is shifting in that direction, and that's what that formula says. Okay, now let's do a math problem. So here, a black body has its maximum intensity at a wavelength of 1 times 10 to the negative 9th meters. What temperature does that correspond to? So you write down what you're given, and you're looking for the T. Okay, you write down your formula. The maximum wavelength is 0.0029 divided by T. Okay, plug in your numbers, solve it for the letter T, and you end up with 2.9 times 10 to the 6th Kelvin. That's 2.9 million Kelvin. So that is very, very hot. So we now have a formula that relates the sideways part of the graph to the temperature. I wonder if there's not a formula that would relate the up and down part to temperature, and yes, there is. So, come on, there we go. So how does the brightness change? That's going to be given by Stefan's law. So F is the apparent brightness of the black body, and it's going to be equal to sigma. So that's this thing here. So that's a Greek letter S, and that stands for the Stefan-Boltzmann constant. So it's a fundamental constant of nature and is equal to 5.67 times 10 to the negative 8th watts per meter squared, Kelvin raised to the 4th power. Don't worry about it, okay? So this one's got a yellow box around it, so that means I just want you to notice as you increase the temperature, what happens to the F? The F increases. What's the F? The brightness. So as the temperature is increasing, do you notice that the height of the curves is increasing? It's getting brighter. So that's what that formula says. So here is a sample question. If an object becomes 3 times hotter, so the temperature goes up by a factor of 3, what happens to its apparent brightness? So we're going to take the 3T and plug it in, and remember it's raised to the 4th power, so the brightness is not going to increase by 3. It's going to be 3 times 3 times 3 times 3. Did I do that enough? So it's going to be 4 3s multiplied together, and that turns out to be 81. So the new apparent brightness is going to be 81 times brighter than the old one. Not what you expected. So you might have thought if I double the temperature, it's going to double the brightness, but it doesn't. It raises it quite a bit. So, what's the point? Okay, have we ever tested these formulas on something real? Yes, we have. So, for example, this picture shows the theoretical black body. That's the black one. So that's what the black body should be for an object that has the temperature of the sun. And then inside of it, you see what is the real black body for the sun. And do you notice that it pretty much coincides with that black line? So these ideas of a black body curve and the black body formulas, they work for the sun. And then they wanted to try it for the Earth. So for the Earth, they calculated what should the theoretical black body curve look like, and then they actually measured the kinds of light given off by the Earth, and then they plotted that on there, and it didn't work out so well. Well, you can see that there are some parts of it do correspond quite well to the theoretical black body, but it's got a lot of holes in it. Places where there's light should be emitted, but it's not being emitted. So for cooler objects, it doesn't work quite as well as for the hotter objects, but it's still pretty good. Okay, we're going to take a break. When we come back, we're going to do the quiz that goes with this lesson.